So today I'm really pleased to welcome Yoseph Dres from University of Rochester. He's going to be talking about the archaeomagnetic study of Iron Age burnt floor from Botswana, implication for the South Atlantic Anomaly.
Okay, thank you very much for the introduction. Let me start by introducing myself. My name is Yoseph Dres, grad student from University of Rochester, working with Professor John Tarduno. Today, I'm going to talk about our research in Southern Africa. The title of my talk for today is Archeomagnetic Study of Iron Age burnt floors from Botswana and its implication for the South Atlantic Anomaly. Okay, so to start from the Earth's magnetic field. So as we know, the Earth's magnetic field is generated in the liquid outer core due to the convection of liquid iron. And this Earth's magnetic field forms a protective layer which reflects the harmful solar and cosmic radiations reaching to the surface of the Earth. That makes the Earth the habitable planets that we have. And this Earth's magnetic field is dynamic, characterized by different features. Circular variations, magnetic reversals, large-scale anomalies, and other features. So we are more interested on one of the anomalic features of the Earth's magnetic field, which is the South Atlantic magnetic anomaly. So as you can see from this map, the South Atlantic anomaly is a region at which the Earth's magnetic field is at its lowest. So this area spans from Southern Africa, South Atlantic Ocean, and Southern America. And this yellow and green region is what you call is the reverse flex patch, at which the Earth's magnetic field is opposite to the normal field. And here, as you can see from this, the region is the large low shear velocity province of Africa. So here we are trying to explore any possible relationship between these features and the South Atlantic anomaly. The potential relationship between the reverse flex patches, the large low shear province, and the South Atlantic anomaly. So the Earth's magnetic field has weakened significantly, at least for the last 160 years, in which we have the direct measurements. And this decline in Earth's magnetic field is most profound along this southern hemisphere, which is the South Atlantic Anomaly region. But yet, even though this area is very important to understand about the Earth's magnetic field behavior, we have limited data. So the data that comes from volcanic rocks, sediments, archaeological materials, which are like direct measurements, they are more concentrated along the northern hemisphere and more particularly in the south, in Europe, Asia, and some parts of the Northern America. So this map is from Geomagia, showing the directional data distribution and intensity data distributions. So we are trying to make efforts to have to improve the data sets in Southern Africa part. So the Iron Age archaeomagnetism in Southern Africa is very important to understand about the South Atlantic anomaly. The last 1,800 years in Southern Africa is what you call the Iron Age. And this Iron Age is basically classified into three different time periods: the early Iron Age, the middle Iron Age, and the late Iron Age. So the important thing here is during this time period, several migration brought the Bantu-speaking peoples to Southern Africa. As you can see from this figure, which is the Limpopo Valley, this is a fertile land in which is suitable for agricultural practice. And these Bantu-speaking peoples are known by their agricultural practice. So they migrated from Eastern and Central Africa toward the Southern Africa, and then they settled. They built different structures like houses for living, grain bins, something like this, for storing their crops, and corral enclosures for cattle keeping. So when the time comes, some droughts or famines, they burned these structures, and we left this kind of floors so that we extract, because these floors are contain clay materials, and we extract oriented samples from these floors and analyze these materials, because we found these archaeological materials are a good recorder for the Earth's magnetic field during that time period. So Tarduno et al. 2015 presented the first archeomagnetic data in this region, both intensity and directional data for the time period of 1000 to 1680. So here we have the directional data. So they determine the rate at which the Earth's magnetic field is changing within this rate. So they start from 1000 to 1050 around 80, and they're trying to determine the degree at which the field direction is changed. So we have here 0.06 degree per year, 0.11, 0.1. So that means it's increasing directional changes of the Earth's magnetic field. So when we compare this observed directional changes with the modern field, which is about 0.07 degree per year, so it shows during this Iron Age, we have rapid directional changes within this South African area. So supports this, they also provide high intensity results in this time period. Basically, at about 1,250 AD, they identified a rapid decline or maximum decline of paleointensity at a rate of about 0.054 microtesla per year. Again, when we compare this this intensity drop with the modern rates, which is about 0.0636 microtesla, so the decline is more profound during this time period. So both this directional and intensity variations of the Earth's magnetic field during that time period may be associated with the recurrence of the recurrence nature of the South Atlantic Anomaly. This is the radial component of the Earth's magnetic field, at which the large low severity provenance is outlined here. And this is the topography of this large low severity provenance. And here they present a model at which how this large low severity provenance may affect the Earth's magnetic field. And the red lines are the magnetic field lines, while the black lines are the fluid flow directions. So they kind of identify the Earth's magnetic field in this region with magnetic induction equations. From this magnetic induction equation, we have the advection term, which is more associated with the fluid flow, that means the dominant Earth's magnetic field, and this diffusion term is associated with the magnetic field spread out of the or weakened over time due to this magnetic expulsion nature. So why? Because this diffusion term is important. We are talking about a smaller scale. So this may, especially in this large low severity province H, while the L is smaller, so the field can change quickly in this region. So they use the magnetic induction equation just to describe how the Earth's magnetic field might look like in this region. So later on, Hare et al. 2008, they expand the directional data in this region to better understand about the secular variation paths. So again, in this work, they identified different directional changes, but if you see this one, there is a time an age gap, even though it shows modest change in directional changes, but still we kind of see some data gaps in this region. So we are trying to fill the gaps and then to improve the directional changes in this Southern Africa area. So they also identify some rapid changes in this late Iron Age, and yeah, so all these rates are by far faster than the modern rate of changes in this region. So we are continuing effort to have more improved data on this Southern Africa, so that we can have refined secular variation paths and intensity data. So in this study, we are more focused on two localities. These localities are it has been done by Hare et al. So our study in this time is more focused on these Magagarape Hills, which is found in Botswana in these Rhino mines. Basically, the Rhino mines we have the directional data, but we don't have the power intensity data. And for this one, we are doing both intensity and directional data. So for now, the age for this Magagarape Hill is dating to 800 to 1000 Common Era, and the Reno mine is dating back to 750 to 800 Common Era. So we conduct a series of magnetism, directional, and high intensity analysis for these sites. Yeah, so basically we have facilities. I presented here the one that I'm using for this project actually. So we start from rock magnetism to characterize our magnetic core minerals and their domain states, and if it is suitable or not for our further experiments. So we start from magnetic susceptibility measurements. We have both low temperature and high temperature measurements. We use the Agiko KLY capability machines for this experiment, and we do have hysteresis loop measurements and first order reversal curves. We have AGFM machines for this experiments as well. So once we have a clear understanding about the magnetic behavior of our samples, we classify good samples for further experiments. And then we have here the demagnetization. We employed both thermal demagnetization and alternative demagnetization. The thermal demagnetization, it goes from 0 to 625 degrees Celsius. Sometimes we use 580 degrees Celsius, depending on the nature of our materials. And we have alternative demagnetization. We use from 0 to 100 millitesla peak fields. And then we have paleointensity experiments. We use a modified Tally methods. So we have the 2G skewed magnetometers with a background field of less than 200 nanotesla. So we measure our NRMs in this machine. So here I have some rock magnetic data. So this one is the magnetic susceptibility with both low temperature and high temperature. So from the low temperature, we kind of getting information about the possible presence of low temperature transition. To kind of see, for instance, we can see here an inflection which shows the very transitions of magnetite at about 150 degrees Celsius. So, and from the high temperature, as you can see from the heating red line and the cooling the blue line, it shows a rapid susceptibility drop at about 580 degrees Celsius. And this is the behavior of the presence of magnetite. And one more important information here is the heating and the cooling curves, they are reproducible, that means reversible in this case. So we kind of saying the sample is very good to go for paleointensity experiments. So we're doing these experiments, one for identifying the magnetic minerals, and so now the thermal stability of our samples. So all these shows dominantly of some reversible nature. So we identify samples and go to the next step. So these are the magnetic hysteresis loops, just the representative loops. So as you can see from this, the shape of the hysteresis loop shows a kind of wasp-waisted behavior. So this is a behavior in which when the sample contains both high and low coercivity minerals. Again, this is also shows this wasp-waisted kind of behavior. So here is the data plot, the remanence, the saturation, remanence and saturation ratio versus the HCR and H ratio. So we kind of see the domain states of our samples. So most of our samples lies in the pseudo-single-domain states, which is typical for these burned materials. So to have more detailed information, we conducted a series of fork analysis. So this is the vertical shows the magnetic interaction, whereas the horizontal shows the coercivity of these samples. So as you can see in these fork diagrams, most of the forks shows pseudo-single domain behaviors, and the magnetite and titanomagnetite are the dominant magnetic minerals in our samples. So the next step, once we identify our magnetic minerals and their domain states, we conducted demagnetizations, a series of demagnetizations, starting with alternative field demagnetization. So these red lines are inclination, whereas these are the declination. And this is the NRM value before doing any demagnetization measurements. So the alternative demagnetization data shows a single component magnetization, which is very stable and unidirectional data. And for most of the samples, the NRM are not fully removed at the peak field of 100 millitesla. So this indicates that there is a high coercivity mineral in our sample. So most of the alternative field demagnetization data orthogonal plots shows the same pattern, having a unidirectional direction towards the origin. The other thing is thermal demagnetization. So from this thermal demagnetization, the same thing, the red lines are inclinations and the blues are the declinations. So the thermal demagnetization data shows a clear line decay towards the origin, starting about sometimes 400, sometimes 450. So this shows the characteristic remanent magnetization, whereas this low temperature component shows some secondary overprints, likely viscous remanent magnetization. So most of our samples demagnetized at about 580, which is again evidence for the magnetite, but we have some samples which goes beyond 580. So this may be this is the evidence for the presence of minor hematites in our sample. So for this image, we have three sites, and we kind of see the distribution of poles in these sites, and all these sites have a good clustering, and we effectively identify the characteristic remanent directions for these sites, and then we calculate the overall direction, and then we incorporate our new data into the existing polycircular variation paths to see if any change in directions is observed. So previously, in the previous Hare et al. Paper, the path was going from here to here, and as you can see, there was a large gap in time. So we kind of refining this gap with a new data sets, and our new data set lies over here and having a new rates which is higher than the previous 0.12 degree per year. So, and again, here we have 0.06 degree per year. So again, even though we have these new data sets, still the age is from 800 to 1000, which means huge age range. So we have our collaborators, archaeologists are working on this to refine, to have more refined age for these MH samples so that we can have a clear loop that shows the behavior of the Earth's magnetic field in this region. And we are we keep doing on this stuff to have more advanced or more improved paths for this region. This is the time versus rates of change of the Earth's magnetic field direction. So this the bar shows the time span, the age, and the rate. And this arrow shows magnetic jerk, which is the sharp decline of the Earth's R2 intensity. And we kind of see if this jerk is aligned with the direction, the rate of direction that we identified. So the previous work has identified some rates associated with the prediction models, and our new data lies along this and this gold color shows the new data. So if you see the magnetic jerks, they are associated with the high rate of change. If you see this, especially these two arrows shows consistent with rapid change in directions. So we are kind of having more data so that we can have a clear understanding about how these things are related with each other. So next we go to the paleointensity. We have here the preliminary paleointensity results for those two sizes, the Reno mines and the Magagarape Hills. So here I have a very good array process showing the paleointensity results. We use the modified tally method. So this is the NRM loss versus the TRM gain. And we have the applied field 24 microtesla. So the slope of this times the known field, which is the applied field, we get the Paleomagnetic intensity during the time period. So here we have 36.7 plus or minus 1.8 microtesla. And again, here we have 33.2 plus or minus 2.6 microtesla. And again, we have here 30.8 plus or minus 2.9 microtesla. So kind of constant values in these sites. We apply a strict selection criteria for all these experiments, including the PTRM checks, and samples passing all the selection criteria has a percentage of 67%, and the average Paleomagnetic intensity data for this Reno mine is 33.2 plus or minus 1.1 microtesla. So this is another preliminary Paleomagnetic intensity data for another sites, which is Magagarape Hills. The same approach, the same technique. So we found 34.1 plus or minus 1.7 microtesla here, and 30.3 plus or minus 1.6 microtesla here. So kind of constant values in this time period. But here the success rate is down to 29%. And the average Paleomagnetic intensity result is 33.3 plus or minus 0.8 microtesla. Okay, so this is the intensity versus year. So this was the intensity data that has been done by Tarduno in 2050, and we put our new data sets over here. So we have two alternatives in this case. Either the field may not be changed in this time period, or as you can see the bar, we have still the huge edge range. So that may be also another reason, because these two data sets shows a kind of consistent Earth-magnetic field. So we're pushing to have more data in this time period, so that we have some good data, so that we have a good understanding about the South Atlantic Anomaly regions. Yeah, that's it. Thanks so much.
Thank you very much for your talk. Big round of applause. So we open the floor now for questions. If people have any, please raise your hands. We can start maybe from your sampling. Can you please take back to the slides where you show the sampling?
This one?
Yeah, the picture. So I was curious about the technique used to orient in situ the floor, kind of.
Okay. Let's go from this one, right? Okay, so this is the floor of the hut or something like that. So we use the northern. Then we take, actually I haven't been in the field.
Okay.
So yeah, it's the plan is to go for next. So I've been working on the sample that we have, but what I understood is this is the samples that have been burned, and we align towards the nodes and take these samples, extract them, and preserve that noising, and then in the lab we cut our cubes based on that nodes arrows, and then we have data collected during the field work. So we use those things to make some corrections, to make geographic correction and things like that.
Thank you. The question came because I saw that the intensity is so high that maybe there's some deviation due to the magnetic compass. So maybe if you go back to the field, it would be interesting to try and do like a sun orientation or something that is independent from the field.
Yeah. We have all the information documented, the sun angle and everything. So yeah, we are kind of using those field informations to incorporate during our calculation stuff. So yeah, I think.
Okay, thank you. So any other question from the audience?
I had a question. Joseph, I enjoyed your talk. Maybe I missed it, but using some of the existing models during the Iron Age, where do we think the South Atlantic anomaly was sitting? And maybe even do we have a sense of if it was moving and what direction it might have been moving sort of during the time period that you're collecting you're looking at your samples?
Okay, so you mean like where was the South Atlantic anomaly during the Iron Age? That's the
Yeah,
samples are taken
exactly.
now.
And sort of like what direction, if it kind of it's moving, right? And sort of
Yeah,
what
yeah, yeah,
direction
yeah,
was it
yeah,
moving during that time period?
yeah, yeah. Okay, yeah. So the South Atlantic anomaly is moving towards the west. That's we know from the model. So it's it moves towards so initially it was there was hypothesis. It starts from the southern edge of the South Africa edge, and then it moves towards the South Atlantic Anomaly, and then towards the Southern America kind of things. So I would say it moves toward the west in general. It's-
Okay, thanks. Yeah.
Okay, thanks, Richard. Is there any other question from the audience? You can also type it in the chat and I will read it out for you. So I guess it can follow up another question from what Richard also was mentioning about the models. So if you can move to the part where you compare your data to the model. Yeah.
Okay, the intensity data.
Yes, please.
Okay, this one.
Yeah.
Yeah,
So I guess one question I have is if you considered also the other models that are available. For instance, our model with the Javier and Pablo Carrasco from, which is based only on Africa data. Obviously, there is not enough data to constrain the field in a reliable way for the same area in the same time, but we did this paper in 22 where we tried to do the curve, a circular correlation curve, also with intensity, I guess. But it's interesting to see how your data would compare.
Yeah,
I can send you the data.
okay, yeah. I'll use that, and then
Okay.
I'll see how it looks like.
Thanks.
Thank you.
So Andrei has a hands up. Yes, Andrei, please. You can unmute yourself.
Okay, sorry for that. I was
you're
talking
back.
without
Andrei's
the
back.
microphone. Yeah. Okay, Joseph, sorry for that, colleagues. I didn't notice. Great talk, Joseph. Thank you very much, and hard work, I believe. I was just wondering about your paleo-intensities in slide 18 and 19. Could you get back them? And
Yeah.
what happened below 400 degrees centigrade?
Oh, 400
You show orthogonal plot from room temperature, but you only show paleo intensity above 400. What happened below?
Okay, yeah, that's a great question. Because I didn't prove that because that's viscous components and the secondary orphan. So that's not important for our paleo intensity calculations. So that's I start from 400 up to like 580 or 600 to take.
Do you have any specific reason for that?
Not actually, just to have I can kind of put them all, but I believe they may not be helpful to have them in this code. Yeah, that's why. But yeah.
Because my point is that actually you erase half of your remanence below 400, but you did not consider this segment for paleo intensity, and that needs to be justified, in my opinion. Yeah?
Okay. Yeah. But most of our samples shows especially during the low temperature steps.
Okay.
They show the overprints, so that
Yeah.
okay, these are overprints.
Yeah.
They mean with our Paleontology results, because we kind of seeing the more characteristic one, that means the more primary one. That's why I excluded those low temperature steps for now.
Okay, thank you very much. Good luck with your further work.
Thank you.
Thank you.
Thank you, Andrei, and thanks, Joseph, for answering all the questions. So if there is any other question from the audience? Well, your presentation was very clear, and it's clearly show a lot of work has been done, and some still to do. So that's yeah.
Yeah, actually, it's a continue. Yeah, we are working on more samples. Even we are more collecting more samples, so that's yeah, we can have more data in this region. And these are preliminary results to show how the samples are. Yeah.
So yeah, thank you very much. I don't know if there is any other question from the audience. Maybe not. So I want to give you another big round of applause. Thank you very much.
Thank you for inviting me.
And thank you for giving the talk, and I hope people enjoyed it. And yeah, these talks is gonna be together with the previous ones on the YouTube. So people can rewatch it and probably contact you if they have any other question. And maybe have another one follow up next year with more data.
Yeah. That's right.
Yeah, so thank you very much again.
Yeah, thank you so much.